Okay. Now, yeah, normally I study mountain belts. And so normally when I give these sorts of talks, I say, why do I study mountain belts? And it's because I get to go to places like this. This is the Bergell in the Central Alps, so the Swiss Alps. And this is where I did my PhD work now. And yeah, you can see that it's spectacular. And really the reason why I got into geology and study mountain belts is to go to these sorts of places and visit these sorts of places in the world. But realistically, there's a whole reason to study mountain belts besides just going on nice field trips. They modulate climate through weathering reactions. So this is the idea that minerals in rocks, as they're exposed, react to carbon dioxide in the atmosphere, and that ultimately draws carbon dioxide out of the atmosphere. Sediment is sourced from mountain belts, so if we're going to understand sedimentary basins, we need to understand where the sediment is coming from. Exhumation of mountain belts, so this is the motion of rock towards the surface, as opposed to denudation, which is more the lowering of surfaces. Exhumation is the opposite, effectively, but it's the same sort of thing, it's the erosion. Exhumation brings rocks from depth to the surface, and it's really through this process that we're able to understand what the rocks look like at depth. Right? If they didn't come to the surface in mountain belts, we wouldn't know what they look like. In terms of natural resources, today, lots of copper, lithium, the things that we need are found in mountain belts. And then there's also seismic hazards associated with mountains and growing mountains. And very recently, people have started to focus more on mountain belts and speciation and thinking about how mountain belts control biodiversity. And that's sort of a really sort of blossoming field at the moment that's really only sort of started to, I guess in the last sort of 3 years, people have really started to think about it. Probably as a result of COVID, I guess. So this is a very famous cross-section through the Alps, and it shows these naps. These are basically slithers of the oceanic or sediments on the oceanic crust as it was subducting underneath the Alps that have been scraped off and stacked on top of each other to produce these famous naps. And this is a sandbox model simulating that same sort of process. And I'm showing this really just to highlight this relationship between erosion and mountain belts. So here, this is sand that's just colored to show you how it's deforming. And there's a piece of material at the bottom that's dragging the sand from the left to the right. And as the sand is being dragged, it sort of slams into this backstop, and these thrust faults develop. And the thrust faults develop, and initially when the model starts, these thrust faults develop and migrate towards the left. But then over time, the sand grows above this black line, and effectively this represents surface erosion. And in this case, somebody comes along with a vacuum cleaner. It's probably a student that's vacuum cleaning this. As the sand grows above this black line, it's being removed. And that process is simulating erosion. And hopefully what you can see is that as the material starts to be eroded, we have the end of this sort of propagation of thrusting towards the left, and we have sort of rapid exhumation and the exposure of these deep rocks in the core of this sandbox model. Okay, have you seen this sort of thing before? Is this? I'm not sure what people know. So if something's unfamiliar, please interrupt. Of course, this actually takes a very long length of time. The sand is moved very, very slowly, and a student would have to be here for the best part of 2 days removing the sand. This is a slow process. Okay. Fortunately, we can also do the same sort of thing using numerical models. So this is a T-box, well, it's a bit complicated, but essentially this top panel is a numerical model simulating the processes that drive erosion. So simulating the development of rivers and sediment transport by rivers out of the mountain belt. And this bottom panel is showing how the crust is deforming as the rocks collide. And the reason why I'm showing this is to get across this idea that the climate and changes in climate can change the precipitation, and that change in precipitation can change how the mountain belt deforms. So during this middle period of time, between 20 million years and 40 million years, there's enhanced precipitation, and that leads to higher rates of runoff and more erosion, and the mountain range actually becomes narrower. Okay, and this is because the faults that are controlling the size of the mountain range have to respond to that change of mass. So ultimately, the faults are slipping only when the conditions are right for them to slip. So only when there's the correct stress conditions. Okay, so we would like to understand mountain belts and erosional processes to understand how erosion rates and tectonics are linked in mountain belts. This idea that erosion can actually influence the tectonics is probably something that really came about in the mid-90s, and lots of people have been trying to solve this for a long time. And this is something that I'm still working on.